just a little early, but there was a question about, I've gotten a few questions about the midterm. And I just responded to one, so I wanted to say what I said to one of the students. Question on inner homomorphisms. And I just mentioned that there's any group G, there's a homomorphism from G to its group of automorphisms. Here, aught G is a group of automorphisms of G. So isomorphisms from G to itself. So what you do is you take G and you send it to just conjugation by G. So you send it to the map, I'll call it C sub G. Where C sub G, probably need to do it with its inverse or something in order for it to be morphism. Probably something like this. Anyway, this or its inverse, I don't know. I mean, either this or G. But one of them is the doesn't matter. Anyway, the point is that the image of this, of the C, the image of C is the set of automorphisms. So the point being that if you're looking for inner automorphisms, it's going to be a quotient group of your original group, because we have this first isomorphism theorem that says that if you look at the image of any homomorphism, it's isomorphic to the quotient of that group by the kernel. So this gives you a description of if you want to count them, for example. It gives you a way of thinking about how you can count them. So I said that more or less to one of the students. If people have more questions, I don't know. I'll tell you what, if I get more questions and I respond, I'll put them in some discussion thing on Canvas so everyone can see it. Anyone have any advantage? All right. Okay. So last time, we sort of stopped at the point where we were talking about, maybe one of the interests that we had and why we had an interest in polynomial rings. And that'll continue for a little while. Polynomial rings are sort of a centerpiece of theory. So certainly worth looking at and studying. But today, I want to kind of develop a little more of the basics of rings. So in particular, we need to know a few of the things that we had for groups are still around, but we have to change them slightly. One is a ring homomorphism. Of course, there's isomorphism as well. And so let's say we have two rings. B, we have a map. This is a function. One ring to another. Satisfy, so ring homomorphism must satisfy the following. So it should be compatible with all of the operations that we have. And what that means is that if we look at the image of a product of two elements in R, then it's going to be the product of the images in R prime. And similarly, we have kind of a homomorphism on the level of abelian groups of addition. We want it to be compatible with addition, in other words. And They also insist on one more property, which is not always, again, not always insist. People don't always insist on this, but we will, which is that it takes the multiplicative identity R, gives us R prime, multiplicative identity R. These are sometimes called unital ring homomorphisms. So let's look at some examples. Well, we've seen one before. We can take, if we just look at the group homomorphism of modding out by n, in other words, modding out by n times z. This is also it's a ring homomorphism. That's an example. That's a surjective homomorphism. There's plenty of injective homomorphisms. So we could take, for example, we could look at all of the complex numbers and map them into diagonal matrices, say n by n diagonal matrices with adjacency, lambda, diagonal 0 to whatever else, is a ring homomorphism. And a big one, which is already maybe seen a little bit, is this notion of evaluation. So you can do this with continuous functions, you can do this with functions, but we'll most commonly think of polynomials. Have polynomial ring with coefficients in R, map to R by just taking X, evaluating, or maybe evaluating at some ring of some fixed R. Okay. All right, so just like for groups, ring homomorphisms allow us to connect different rings, allow us to relate one algebraic structure to another. And this is what makes the subject very rich, is being able to play ideas between off different structures. So there's this proposition I mentioned, it's called the substitution principle by Arden. I'm guessing it's more of like a universal property type of a fact, actually. So you might not see, if you see this in a higher level course, it might not be called substitution principle, but okay. Let me see what it is. It is sort of important. It gives you a way of defining a bunch of ring homomorphisms if you want them. But it says, okay, suppose we have one ring homomorphism that we're given, and an example would you could just take the identity. And that R X be the ring of polynomials. With coefficients. R. Okay. And it says the following thing. If you choose any element alpha in R prime, there is a unique homomorphism, ring homomorphism, I say homomorphism in the context of rings, it means ring homomorphism. Capital V, it's ending Rx R prime, which agrees with lowercase v constants, constant polynomials, sends x and then B is just sort of a more general version. So more general. You take alpha 1, say alpha n, in R prime, and the same statement above. I'll say similar, not same, similar statement to the multivariable ring polynomials. There is a ring homomorphism from the ring polynomials with n variables R prime, where alpha I is mapped, xi is mapped to alpha I. These rings, by the way, are of great interest historically and currently in mathematics. And they should be of great interest to you even if you don't find math that interesting and are really just looking for a tool. Because, you know, zero loci of these things describes all sorts of geometries, and you can basically, whatever kinds of algebraic constraints you might put on any system, can be, if they're defined with polynomials, can be defined as oftentimes by studying it. That ring. It's like part of algebra. Very big subject. Let's see. So what is this? What does this proposition say? What do people think? The way of thinking about this. So how can we prove this? Let's try that. Let's just do A. Proof of A. So A is saying two things, right? It's saying that there exists something and that it's unique. To prove a statement like that, you really do need to address both of those points. So maybe start with existence. So how would we prove existence? How would we show that? Can you define it, like on the notes? It doesn't?
No. I was saying, could you start by assuming that it doesn't? Proof by contradiction.
It's a harder proof by contradiction. There aren't that many proofs like that. There are some. Explain theorems. So it's a harder proof. This one's you're making it too hard. This one is more like you can do it concrete. Like let's just do it concrete. So this is you're asserting the existence of this homomorphism. And we have some requirements. We have that it's phi on constants and it sends x to alpha. Well, let's take an arbitrary element of this and sort of see what those requirements tell us. Let's suppose this is just do it. Suppose f of x is equal to a naught plus a1x. All of our polynomials look like this. Take b of f of x. It has to be a polynomial, and it sends constants, here's the constant term, to phi of a naught. So phi of a naught, lowercase. And sends x to alpha. But what about this guy? Where does it go? Well, this is in R, and we want to map it to R prime. So this is in the image of this. So this whole thing should be in R prime. I can't stay in R. R prime could be a completely different ring.
Yeah. So is it just phi of A1?
It has to be. It must be. Right? Because we know that A1 is a constant. If I take it by itself, that goes to phi of A1. I know that X goes to alpha. So, and this is a ring, I'm going to posit that this is a ring homomorphism. So it has to send the product of these two to the product of these two. Okay, and then that should give us a hint as to what happens, you know, for here we should have phi of A2. I didn't write A2, but okay. Alpha squared plus phi of AN, alpha to the n. So exercise, this is a homomorphism. Ring homomorphism. I don't want to, it's just routine. But, you know, maybe worth doing. Yeah, some extra time. And then uniqueness. Well, suppose we have some other guy. Suppose prime satisfies conditions. And namely sends x to but and constants to phi of whatever they are. Then, well, as I said, you know, you could say AI and x to the I is equal to phi AI, phi x to I. This is equal to, by the conditions. So then taking sums gives us that this should be phi prime. Gives us that phi prime, same as phi, capital Phi primes. Okay. I mean, taking like any polynomial can be written this way, a sum of these types. Copy the students up to me. I'm supposed to do private. And how am I not disturbable and still disturbable? That's why old people are obsolete. All right, now I'm not disturbable. Good. Okay. So what are some examples of this? So one example of this is kind of, is used quite a bit actually in algebra and in studying rings. And that's just reducing the constants. So if you have a ring, say over the integers, so, or sorry, ring of polynomials with coefficients the integers, we can then take this and we can reduce, reduce the coefficients to being mod n. So this gives us a surjective homomorphism. By this theorem, by the proposition. Here, we just send x to x. X is sent to x. Constants sent to, constant a. A mod n. I don't know what this is. So in other words, you take a polynomial and you reduce all the coefficients just to mod n. Start talking about polynomials mod n. Very common thing. Okay, so there's some other theorems here. There are a lot of little, well, there's one, actually only one more little theorem here, which is just, I guess this is kind of reasonable. I'll just say it and you guys can tell me. So let R be a ring. There is exactly one ring homomorphism integers to R. In other words, the key word is exactly. There's no more, less. Call it I. What is it? Why is it unique? You guys tell me anything about it? Tell me anything about a ring homomorphism. One ring to another. You know anything about, just from the properties, you know anything about these? Say, street came up to you and said, tell me about ring homomorphism. Good. You're like, oh yeah. I do this. What about group homomorphisms? What do you know about that?
So they preserve the operation.
Right.
Phi of A B equals stable.
Okay, so yeah. Can you tell me anything else? Could you tell me where an element is sent? Any element? A given element, a special element.
Given the homomorphism, yeah.
What if I just said I have a homomorphism? Can you say one thing about it? That can you give me one element you know where it goes? Again, what about ring homomorphisms? By definition, multiplicative identity goes to the additive identity. Okay.
Should also go to the additive identity because of the addition property.
Yeah, well, it's a homomorphism of groups, and you can prove, as we did, that when you have a homomorphism of groups, identity has to go there. You don't have to insist on that. That happens. So you know the identities go to the identity. So that means that if I'm looking for this homomorphism, one here has to go to one here. tell me about 1 in the integers. What does 1 give you? 1 gives you a generator, right? 1 is a generator of the additive group of integers. So any integer is 1 plus 1 plus 1 positive integer that many times, right? So b of n equals b of 1 plus 1 and time. This is a homomorphism. I'm sorry, phi, I. I is any homomorphism. I will do this. That's I1. You can talk about n times. This means multiply by, add it to itself that many times. This n is not an element of R. This just means multiply that. In other words, but this is, as we saw, I1 must be 1, so this is n. We don't have any choice of where n goes. It has to go to n times whatever that multiplicative identity is of R. That's it. No other choice. And of course, we have inverses. This is a ring homomorphism, so an abelian group is a group homomorphism. So if n is negative, it's just the additive inverse of this. So that's the only one. And it is a ring homomorphism, as you can check. There's a fancy, very fancy, too fancy for you guys, but I'm going to say it anyway, way of saying this. There's this whole subject in math called category theory. I don't know, maybe some people have heard of it. And anyone heard of category theory? Okay, so 1. So, well, if you do computer science, you might bump into it because it's sort of taken over parts of logic and specifically parts of design, so like type theory and that kind of stuff. Anyway, this is in categorical terms. This is saying that the integers is an initial object in the category rings. Fancy version. Category theory basically takes subjects in math and makes them into mathematical category rings or category groups, and so on. You talk about functors between relationships. Very nice stuff. Very beautiful. Founder of category theory, one of the founders, claimed category theory was not like not loved by a lot of mathematicians. Sort of debatable. Nowadays, it's universally accepted, I would say. Well, not universally, but the vast majority of them admit that it's totally reasonable. Anyway, my mother is a mathematician. She went to graduate school at the University of Chicago, where McLean was, and hated the subject of category theory because she was insulted by McLean in the copy room. She was a postdoc, and so he just said, "Hey, I need the copy machine. Get out of here." And so she left. But then she hated category theory for it, which shows you the seriousness of slighting your mother. She will disavow your whole subject. Okay. Now, ring homomorphisms, just like group homomorphisms, have kernels. And so we can talk about the kernel of a ring homomorphism. And what we saw with group homomorphisms is that the kernel of a homomorphism is a subgroup of the group that's our domain. But it's not just a subgroup. It had an additional property that not all subgroups share. To guys remember? I have a homomorphism between groups. Kernel of F, this is a subgroup, G. Is it any old subgroup? It has special properties. That's superpowers. What is a superpower? Huh?
What did you say, sorry?
What is the like extra property? It's not any old subgroup. It's
every element is like that.
Okay, so yes, certainly that's the definition. But does it have an extra property? Okay, we have some properties of subgroups. What are properties? We have the trivial groups, that means they're one or everything. Then some subgroups are with center, like the center is a special subgroup. And then there are other subgroups that we call something special. Or maybe not that, I don't know. We call them something. I don't want to say because I'm not going to give you an answer. But you guys remember when we did subgroups, we did left cosets, right? We talked about the set of left cosets, partitioned it. I said, this is a set of left cosets. It would be nice if we could make a group out of this set. And we can, but we can only do that if the subgroup that we're considering is X is the number of them. So, but yeah, good. On midterms. Give me the answer, right? Guaranteed 100%. Well, when can we define a quotient group? Can we do it? We cannot do it with every subgroup. There's only these special subgroups that satisfy this property that we can actually define a quotient group. If we tried to define a quotient group for an arbitrary group that did not satisfy this property, we would not have a well-defined operation, multiplication on the cosets.
Like a non-empty kernel.
Oh, is it a normal subgroup?
There we go, a normal. Normal. Special, normal, whatever. Right? Normal. That's this notion. A notion of normality, right? This is a normal subgroup. Now, we want the same thing for rings. We want our kernels for ring homomorphisms. They're not going to be any old, the sub things of our ring. They're going to be things that we can actually quotient by. And there we have a special name for these things. They are subrings without a unit generally, but they're more, you should never think of them as subrings. You should think of them as these special things that we call an ideal. An ideal ring non-empty subset. I. It's written in the same kind of notation as sometimes as that of normal subgroup. Satisfying a couple of properties. One, I is a subgroup, additive subgroup, meaning under addition, it's in the subgroup. And two, kind of a weird looking one, says for every R and R, A, I multiply R and A together, so I should probably also, so this is the, well, let me write it down and I'll do it. So as I've said, rings don't have to be commutative. Multiplication does not have to be commutative. So we would want to include this as well. But sometimes this is also called a two-sided ideal. If you have a non-commutative ring, and people will certainly leave off this condition and talk about left ideals or right ideals. So anyway, I'm just talking about an ideal. And if you want, you can consider part of the commutative, just simplify. So why are ideals present? Well, as I said, these are kernels are ideals. So maybe this is the first. So there's some examples. One, and maybe the most important example, is let a phi be a homomorphism of rings. Well, what is kernel of phi here? This is equal to the set of elements mapping to 0 in R. So all of the elements in R, so when you look at their image, it's 0. That's really the kernel of the group homomorphism under addition. That's the way you can think of it. Then this is an ideal. Oops. As you can see, if you multiplied one of these lowercase r's by any element, I mean, it's certainly an additive subgroup because it's a kernel of an additive group homomorphism. But furthermore, if I take, S times R, this is phi of S, phi of R, this is phi of S times 0. Anything times 0 is 0 in a ring, as you can easily prove. So kernels are ideals. Ideals are like sort of these very beautiful abstractions of sort of elements in some sense. That's how that's where they get their name. It's that back in the early days of algebra, there was a notion of trying to say we want to idealize elements, make elements that satisfy properties that we would hope for, like the fundamental theorem of arithmetic. And ideals were born out of that kind of approach. Okay, what are other ideals? There are things called principal ideals. These are very simple ideals. You take an element, so if A is an element of R, consider just all of the multiples of A. I think he really defines, I'm looking at the definition from, he does really define the left ideal more than an ideal. But okay, so this would be a left ideal. Maybe consider this commutative for now. You just take all multiples of A. Left ideal. All right. So some precise examples, like if you were thinking of the integers, you could talk about 2. It's just all multiples, all of the evens, right? This is even number. That's an ideal. Also the kernel of sigma 2. You can then, you can just talk about ideals generated by a finite number. So you don't have to. I'll use A instead of X. So polynomials. So this would be denoted A1, AN, and again, I'll talk about the left ideal. You just take all possible kind of linear combinations of these elements, where now you allow the coefficients to be any elements in your ring. This is a left. This is an ideal as well. The study of ideals was very, very intense in the early part of the late part of the 1800s, the early part of the 1900s, and really, I would say more than anything was the sort of beginning of modern algebra, the way we think of algebra today. The leaders were people like Hilbert and Noether. I mean Noether. And these are like two of the best mathematicians in the early part of the 20th century. Anyway. All right, so let's get some facts about ideals. So there's several propositions. I won't make it through all of them, but let's a few and get an idea. So one is deals with ideals of fields. Only fields of a field zero ideal, unit ideal. The unit ideal is everything. So, in other words, it's the principal ideal with the multiplicative identity. Zero ideal is what you think it is. It's just zero. And then the other is that it's sort of a converse. So I'll just say it this way. A ring actually not true. So again, I think here we want, let me assume here R is commutative. This would be true otherwise. I must say that somewhere in the text and I just didn't write it down. So a ring with no non-trivial ideals very kind of abstract way of saying everything is multiplicative inverse. My godfather told me in high school he's also a mathematician. Said that the mafia career choice is a field you can go into. And I said, what do you mean? He said, well, it's a ring of thieves. And they're all from New Jersey, so it's commutative. They all commute. They have no non-trivial ideals. Sorry, sorry for passing that on to you. You can forget that. Okay, that wasn't his point. All right. So why would this be true? What you guys tell me? Why is the proof of what's the proof of A? If I have a field, why don't I have any non-trivial ideas? Let's suppose that F is a field. I see. you tell me? You want to show it's either 0 or everything. Let's assume it's not 0. 0 is 0. If I is not equal to 0, then there's a non-zero element. Right? It's not only 0, then it has to have something not 0. Okay, so what can you tell me about lambda? Lambda is non-zero, it's an element of the field. What can you tell me about
We should be that we should be able to multiply by everything in the field and get something right.
Okay, sure. It's in, okay, so you're telling me about what it means to be an I, but I'm saying, okay, forget about I for a moment. Suppose I have a non-zero element in a field. What can you tell me about that non-zero element, just knowing it's in a field? What's a field? Right, but it has a special property that makes it better than a ring. Muted multiplication and multiplicative inverse, not to be forgotten. Like that's a big property, right? That's not a, so if lambda is an element of I and lambda is non-zero, well, forget about being an I, lambda has an inverse. Lambda inverse is in F. But now the property of being an ideal tells us that 1, which equals lambda inverse lambda, is also in I. All multiples of the elements of I are not. 1 is in I, which means it's a unit ideal. That's that I equals I. If 1's in your ideal, you can multiply anything and get something, you know, that thing in the, so sometimes something times 1 is itself. So everything is in the. Okay, I'll let you do B. There are a couple of other results, but I'm going to get this result, which I think is certainly most important nowadays. One is that, so one I'm skipping over is that if you have a homomorphism from a field to another ring, then, and it's not the 0 map, so the other ring is not the 0 ring, then that's an injective homomorphism. And that follows from this proposition of basically looking at the kernel. If you have a 0 kernel, then it's in. Okay, so I'll skip. So this proposition is the following. So, well, I need a field. So that have to be a field. Every field in the ring of polynomials with coefficients in F is principal. So there's a term for this. So we say, which I don't know if Arden talks about, but we say Fx is a PID, principal ideal domain. There are types of rings that have very nice properties, not shared by others. And the proof of this is like deja vu. Seen this proof, but you've just seen it for another PID. Integers. Classified subgroups of the integers, prove that they all look like n times z plus, right? Where plus is additive groups. It's almost the same proof for this case here. So the idea is the following. I'll just sketch it because I don't have time to do all the details, but it's not hard. So suppose we have an ideal f(x), and it's non-zero. At 0, it's still principal, just principal generated by 0. Not 0. And we can choose f of x, I, to have minimal degree. In other words, it's, when you look at the degrees of all the elements in I, you can certainly find something with the smallest degree. Maybe not unique. Now the claim then is that I equal to f of x. The proof, the claim is that if g, I, then divide by f. We have a division algorithm for polynomials, just like we did for integers. And we can see that R of x is equal to the difference of these two, but g is in I, and this is a multiple of something in I, so it's in I. So, and it's a group under addition, so that's in I, which means R of x is in I. The R of x has degrees strictly smaller than f by the division algorithm. And since f has minimal degree, that means that R has to be 0. And then you're done. If R is 0, then G is a multiple of f. So all of the elements of I. That's a quick, I mean, if you need some more time with it, that's fine. Go ahead and look in our next time. We'll continue from there.